Welcome back, everybody. I'm Jason, and today I'd like to chat about one of the most fascinating numbers in all of math, and that is called Euler's number, commonly known as the number E, as you might see it written in math or even on a calculator. It's right up there, in my opinion, with pi as one of the most important numbers ever. In my opinion, Euler's number E is not only fascinating, it's incredibly useful. You see, when you study calculus and you study algebra, this number E, just like the number pi, it constantly pops up no matter what problem you're solving oftentimes. For instance, it shows up in physics all the time. It shows up quite literally everywhere in quantum mechanics, in engineering classes, electrical engineering, mechanical engineering, even in chemistry in some places. In fact, every sine or cosine function can be written in terms of E. So anytime you have any kind of waving thing going on, whether it's a pressure, or it's an earthquake, or it's electromagnetism, or whatever, if you can write it in terms of a sine or cosine, then you can write it in terms of this really special number E. And that's what we want to talk about today. So Euler's number E is what we call an irrational number in math, just like pi is an irrational number, which means the decimal numbers after the decimal point, they go on and on forever without any repetition of a pattern. And the number E is approximately equal to 2.71828, of course, with decimals that go on forever. And it's irrational, as we mentioned, just like pi. But E is a special number because it comes from a special idea, and that's what we're going to focus on today, and we're going to roll up our sleeves and talk about it. So first, I'd like to talk about a little bit of a historical background before diving into the details. The story of Euler's number E really begins in the 17th century, before Euler was even born. Mathematicians like John Napier were exploring logarithms. That's another math concept that you know is on your calculator. You use it in calculations all the time. And they were studying logarithms to simplify calculations. And I want you to remember for a minute that a logarithm is the inverse function, or what we call the opposite function in math, to an exponential function. But it was Jacob Bernoulli who first encountered the number E while studying compound interest in 1683. So this number that pops up everywhere nowadays actually originally emerged from a seemingly simple question. Of course, all questions seem simple in the beginning. And that question here was, what happens when you compound interest continually? Now I want to stop for just a second and talk about what compounding is anyway. It has applications to everyday life, so it's probably something that you're familiar with. So let's say that you get 5% interest on the money in your bank. That's probably higher than you actually get, but let's use it because it's a nice round number. And let's say that it's compounded yearly. What does that mean? That means that if I give the money to the bank, or whoever I'm talking about, and they hang on to it, and if I let them have it for a year, then at the end of 1 year, that's one compounding period, they are going to give me the interest that I earn on the money I give them. And if it's 5%, that means 5% of 100 is $5. And that means that if I let them hold my money for a whole year, and so that means I can't spend my money, I have to give it to somebody else to hold it, then at the end, they'll give me back my $100, but they'll also give me 5%, which is another $5. So I'll get $105 back. And that's if I hold it for a year. Now, if I let them hold it for another year, then on the balance of whatever they're holding, they'll give me 5% at the end of another year, right? But this compounding period doesn't have to be a year. That's just the easiest thing to think about. You might think about interest that's compounded every month. So if I tell you 5%, but it's not compounded yearly, it's compounded monthly, what that means is every single month they give me a little bit of money, which is kind of better because I don't want to wait a whole year to get some money back. I like to get it monthly. That sounds a lot better. Makes me feel a little more comfortable, right? But you got to remember that I'm not going to give you 5% every month, because then I would be giving you $5, and then the next month it'd be a little bit more than $5. Because remember, if you have $105, then you'd be getting interest on the entire amount for the next month. So the way it's really done is they'll take that 5% if it's compounded monthly, and they'll divide it by 12, 5 divided by 12. That's a much smaller interest amount that you will earn every single month. So you see, by making more compounding periods, what you do is you take the overall interest rate and you divide it by how many compounding periods there are. 12 if it's monthly. But you see, you can go beyond that. You can say, well, what if I want to compound it weekly? Well, there are 52 weeks in a year. So I'm going to give you some money every week, but I'm not going to give you 5% every week. That'd be insane. What I'll do is I'll take the 5% and I'll divide it by 52, and I'll get a tiny interest rate, and I'll give you that amount calculated every single week. And so that's the concept of compounding. The more compounding periods there are, the more often you earn some money, but the interest rate is divided down by the number of compounding periods. So the mathematician that was studying this kind of did a thought experiment. Let's say you invest $1, only $1, at 100% interest, compounding n times per year. What is the limit as n approaches infinity? Now let's just decipher that for a second. What I'm saying is, if I invest $1 and after one compounding period, let's say it's a year, then if I am earning 100% interest, that means that I'm going to have $2 at the end of the compounding period. And if I'm going to instead compound it every month, then I'll take my 100% interest, I'll divide it by 12 because there's 12 months in a year, and that'll be a smaller interest rate, and I'll get that every month. And if I'm going to compound it weekly, I can divide my interest rate by 52 because there's 52 compounding periods, weeks in a year, and I'll do it every week. But then I could think about doing it every day. There's 365 days in a year. But what about every hour? I could calculate how many hours there are in a year. What about every second? I could really calculate how many seconds there are in a year, take my interest rate, which is 100%, divided by the number of seconds in a year, and I get a tiny interest rate, but I'll earn that every single compounding period, every second. But don't forget that when I earn that money, I've now earned slightly more than I had. And so when I go into the next compounding period, I have slightly more money than I had for the first one. And so the mathematical question he was asking is, what happens if I let the number of compounding periods get really small, below a second, maybe a millisecond, maybe a nanosecond, and do it what we call continuously? So when you read mathematical wordiness like this, and you say, what happens to the limit as in the number of compounding periods approaches infinity, that just means what happens if I take $1 at 100% interest, but I let it compound every micro nanosecond, basically continuously all the time. And it turns out that that number approaches what we call the number E. Notice it's a little bit more than 2.71. Notice 100% interest on $1 would give you $2. But when you compound continuously all the time, it approaches more than 2, and it converges to this irrational number called 2.7128, and so on, and this number does not repeat ever as far as the pattern of the numbers after the decimal point. So this financial example is how this number came about, but it turns out that this number, because it deals with exponential functions, which is what interest really can be written as an exponential function, because it's written and important for exponential functions, it has all these applications all over the place that you get into, and you see this number E popping up when you're not even talking about interest. You see it popping up in sines and cosines and other things that I'll tell you about soon. So there was a famous mathematician. His name was Leonard Euler. You may have heard of him. There's Euler's number, there's Euler's theorem. The legend has it that Euler invented so many things in math, so many theorems, so many proofs, so many, corollaries, all these things that were important in mathematics, that they stopped naming things after him, and they started naming them after his students because he was inventing so many things. We didn't want to call everything Euler. So Leonard Euler formalized this number, the number E, Euler's number now, in 1731, and he showed that it was both irrational, which means he proved that, and it cannot be expressed as a fraction. So the decimals go on for and ever without repeating, much like pi does. Now, he proved its importance by connecting it to the fundamental nature of exponential growth. And that's why this number is so important in logarithms and almost every branch of science, because most things have applications to exponential functions. But you might ask the question, why is this number E everywhere? Why do we see it? Here's what makes it special. It's the only number where the derivative of the function e to the x in calculus, where e is Euler's number, e to the x function, that's an exponential function, the derivative of that function is itself. This is a super unique property, and it makes it as the natural base for exponential functions, and as we'll talk about logarithm functions in calculus. Now we have to take a little bit of a side detour in calculus. If you haven't taken calculus yet, that's okay, you'll understand what I'm about to say. But if you have, I think you'll agree about the importance of the number e. So in calculus, about half of calculus 1 is what we use to talk about something called the derivative. You know, in algebra, you learn about the slope of a line. If a line is flat like this, we say the slope is 0. If the slope is something like this, we might say the slope is 1. And as we go steeper and steeper and steeper, the slope is higher and higher. Maybe the slope is 15 and 18 and 22. And if the slope of a line is vertical, we say it's undefined, or you could call it infinity slope if you want. It gets bigger and bigger, eventually being undefined or infinity when it's vertical. That's what we learn in algebra. But in calculus, things are involving curves, because in real life things move along curved trajectories like baseballs or rocket ships or orbits of the planets, and they're not just straight lines. We learn in calculus to find the slope of one of these curves, but the way we define it is the slope of a line tangent to the curve. That means if we want to know the slope of a curve, we pick a point and we find a line that's just barely touching at one spot, and we call that the slope of the line tangent, and whatever that is what we call the derivative. So in calculus, you learn how to find derivatives of all kinds of functions. Parabolas, sine, cosine, tangent, pretty much any function you can think of, we learn how to handle it in calculus. But there's one function that's special, very special. It's usually devoted an entire chapter in calculus 1, and that's the exponential function, which is a number raised to the power of x. Now, if that number, the base, is the number e, Euler's number, which again is very special, then that function is called the natural exponential function. It's so important that we rename the function and we call it the natural exponential function. If the logarithm involves the base with the number e, we call it the natural logarithm because it pops up so often in nature. And when you have this exponential function with the base e, e to the x, it has a shape that looks like many other exponential functions, but it's special because when we take the derivative of this function, meaning the slope of the line tangent everywhere to that function, what do we get back? We get the same function back. So you learn in calculus and you learn to prove that when you take the function e to the power of x and you take its derivative, you get back the same function e to the power of x. And all that really means is that the slope of the line tangent to that function e to the x, the slope of it is equal to the value of the exponential function itself. It's so special because of the relationship between the value of the function e to the x and the slope of the curve of the line tangent to the curve at the same point. And that's why it shows up everywhere, or at least one of the main reasons why it's so important. Now, before we roll up our sleeves and learn further the details, I'd like to share with you some applications in science and engineering. So in the real world, there's something called population growth, like for instance, bacterial growth, viral growth, things like this. And that involves the exponential function e to the power of rt. T is time, which is always positive, and r is a rate. And because it's positive, the bacterial growth is going to increase in an exponential fashion. And so it's related to the Euler number e. It shows up in everything from how we deal with antibiotics, how we deal with sickness, how we deal with population growth of animals, bacteria, when we study complex systems that grow exponentially. Now, if you take that exponent on the e and make it negative, you might have e to the power of negative lambda t. Again, t is time, but lambda is another number, and that exponent is now negative. And that could be radioactive decay. A sample of some radioactive plutonium decays with some rate. That's governed by an exponential decay. So this number that's related to finances and compounding interest is related to exponential growth of populations and exponential decay, for instance, in radiation. In my neck of the woods, in electrical engineering and circuit analysis, you end up with exponentials all the time to model circuits. But the exponential is e to the power of I omega t, where I is the imaginary number. And you learn later that there's a connection between that expression and sine and cosine. So anytime you drive a circuit with a sine wave, or a cosine, which is what comes out of your wall, or an electromagnetic wave, which can be written as a sine or cosine, you can always write it as an exponential with an exponential base e. And in the exponent, you can have a complex number, j omega t or I omega t there. Omega being the frequency and t being time. So quite literally any propagating wave can be related to the exponential number, Euler number E. Just to rattle off some more examples you may have been exposed to, reaction rates in chemistry, the rate of formation of the products, they can be related to these exponential functions. We talked about population growth and decay, but how about sound intensity and sound decay with deadening materials deadening the sound intensity? What about heat dissipation and modeling of financial markets? All of them can be tied back to this Euler number E and the exponential functions that go with them. And let's not forget quantum mechanics. The entire theory is involving what we call a wave function, which has an exponential number E, Euler number E, with a complex exponent and a complex amplitude. So the entire branch of quantum mechanics relies on this Euler number E. So to wrap up this little introduction, we can say that from compound interest all the way to quantum mechanics, Euler's number E keeps appearing because it describes the natural growth and decay perfectly. It's not just another mathematical constant to throw in the bag. This one is really special. It's a fundamental description of how our universe behaves. So now what I'd like to do is roll up our sleeves and dive in a little bit deeper and explore these concepts more fully so you have a solid understanding of Euler's number, not only what it is, but how to use it, why the Euler number involving functions involving Euler number, why they're so important, and how to use them when you're solving problems. Last name is, it looks like the last name is Euler, but actually it's pronounced Euler. So his name is Euler. This is Euler's number. Where does it come from? First of all, let's talk about what this number actually is. So the number E is approximately defined to be the following number, 2.71828 ... Now the reason I have the ... is because the number E is called an irrational number. It's an irrational number just like pi is an irrational number. So the decimals here, they go on and on forever in a non-repeating pattern. I could grab a computer and calculate the number E, Euler's number, to 100 million decimal places if I wanted to, and I would never see any repeating pattern of decimals. Of course, some of the numbers would be repeating, but the pattern would not repeat because it's an irrational number. All right, so in order to understand where the number E comes from, let's take, and why it's useful, let's take just a second to talk about, ultimately, once we know where that number comes from, what are we going to use it for? It's just a number, first of all. When you see the number E or the letter E written in a mathematical equation or formula, in your mind, just replace it with a number. It's just a number that happens to be a very, very special number. We're going to discuss exactly why in just a second. But ultimately, once we know what this number E is, and once you understand where it comes from, we're going to later on define a few very special functions. The first function is, remember we talked about exponential functions. We could have 2 to the power of x. We could have 10 to the power of x. We could have 35 to the power of x. Those are all exponential functions. So a very special exponential function is e to the power of x, where e is just this very special irrational number. I don't expect you to know why this exponential function in particular with this base being 2.71828. E is just a number here, okay? I don't expect you to know why it's important. We're going to study that later, and in fact, we study why it's so important a lot more even in calculus. But just to know that this exponential function with this particular base is extremely important in math. It has very special properties. And because this is the exponential function, and because we now know that logarithms are the inverse function of the exponential function, then if you take this as your exponential function and you create the inverse of this guy, then you might come up with something called the logarithm with a base e of some number x. So these are inverses of each other, but we never write log base e x. What we really do is we have a very special, we have its own name. We call it the natural logarithm. So these two things are exactly the same thing. So if you were to see in an equation somewhere, if you were to see ln of s, ln of x, ln of some number, it means natural log of that number. It just means logarithm with a base e of that number. So the number e as a base is so special that we have its own logarithm for it, and the name of that logarithm is called the natural logarithm. So this is called the natural log. Now you might guess by the name natural log that it's something natural about it. There's something very special about that number. And that's because the number e, as I mentioned before, is that natural number that just pops up when you study exponential growth. It just falls out of the equations, just like the number pi falls out of the equations when we talk about circles. Okay? So what we want to do for the rest of this lesson is start to go down the road of trying to understand where this number e comes from, why it's important, and then in the next couple of lessons we will dive a lot more detail into the natural logarithm and the exponential function. We'll do a lot more detailed work in that area. Now we're going to talk about where this number comes from. Before we go there, what are some other numbers in math that are special, that have these special status? Well, I could argue the number 0 is a very special number. I could argue the number 1 is a very special number. It's number 1 is the first number in a set that denotes the amount of something. The number 0 denotes nothing at all, which is kind of its only, in math, it's its only kind of like special class of number. The number 0 and 1 are both very special. Above and beyond that, there's some other numbers that you all know about that are also very special. For instance, we talked about the number pi. You all know that pi is 3.14159, and it goes on and on and on forever. Where does the number pi come from? The number pi comes from looking at the geometry of circles. If I have some circumference of a circle and I have some known diameter of this circle, then I know that the circumference is pi times the diameter. So pi serves to be a conversion factor. It converts diameters into circles. If I know the diameter of a straight line and I multiply by this very special number, it gives me the length of a circle that would have that diameter going around. That's what we call the circumference. So the reason pi pops up is because it's a feature of our geometry of our universe we live in. It's what relates linear distances to curved circular distances. This is what we call the circumference of a circle. So it comes from geometry. What are some other special numbers in math? All right, the number square root of 2 is also a number that pops up in math quite a bit. We have other radicals, of course, but this one pops up a lot because it comes from the Pythagorean theorem. If I have a right triangle with a length of 1 on one side and a length of side on the other side, length of 1 on the other side, and then I would denote the hypotenuse to be c. This is different than the circumference of a circle here. Then I can write c squared is a squared plus b squared, but this is just 1 squared plus 1 squared. And so what's going to happen here is c squared is going to be, this is 1 plus 1 is 2, and then c is going to be equal to the square root of 2. So the square root of 2 is the very special length that comes when I arrange a triangle like this and measure the diagonal along one side. So again, it comes from geometry. The circumference of a circle comes from geometry. The definition of the square root of 2 is another irrational number that comes from geometry. Okay. What are some other very special numbers? We're not going to go through all of them, but probably the other one that is very, very important is the number I, which is the imaginary number. And this comes from the definition being the square root of -1. So these guys here, these first two definitions of these two irrational numbers, they come from geometry. One comes from looking at how circles behave. One comes from looking at the Pythagorean theorem. Both of these are geometric definitions. This one is not a geometric definition. It's just the definition of the square root of -1. We call this thing the imaginary number I. So these come from geometry. This one comes from a definition. The number E comes from the study of exponential growth. So it's not a geometric definition. It comes from studying how things grow exponentially. And it turns out when you study how things grow exponentially, a number falls out of those equations when you study it, and that number is 2.7182 and then infinite decimals beyond it, and that number has very special applications in math. All right, so in order to figure out where this thing comes from, ultimately, it comes from one way to talk about where it comes from. Actually, I should say there are many ways to approach where Euler's number E comes from. The way we're going to talk about, let's talk about what we've discussed in the past, which is the compound interest formula, which talks about how much money grows over time in terms of an exponential function. We've discussed this extensively in the past. So, recall compound interest. right? And I would say, if you haven't watched my lessons on compound interest, I would highly recommend you do it first because I extensively talked about this formula in the past. But we're going to go ahead and write it down again. The value of money at some time in the future is equal to whatever you invest. We call that the principal, multiplied by 1 plus whatever the annual interest rate is, divided by the number of compounding periods. And this is all raised to the exponent to the number of compounding periods times the time in years. Okay? If you don't know where this formula comes from, if you've never seen it before, it just means you haven't watched my lessons on compound interest. So I highly recommend that you go watch that because I explain exactly where every little part of this equation comes from. But just to make sure we're all on the same page, this is the principal you invest. This is how much money is worth time t years down in the future. R is what we call the annual interest rate. And N is really important. It's the number of compounding per year. So it's how many times I'm compounding per year. If I'm only compounding annually, I'm only getting free money once per year, so then N is 1. If I'm compounding 2 times a year, then N is 2. If I'm compounding quarterly, 4 times a year, then N is equal to 4. So this is the equation that governs how much money you're going to have in the future when I give you growth at a certain interest rate compounded so many times per year. That's what this is. And this number is ultimately going to allow us to calculate this very special exponential base that we call E, which is Euler's number. So here's how we're going to tackle this, all right? Let's say I'm a bank, and I'm going to give you an excellent deal. I'm going to give you an amazing deal, the deal of the century. What I'm going to do is I'm going to give you 100% interest rate, which isn't really not going to ever happen. Normally, interest rates in real life are 5%, 6% interest per year, something like this. But that's not the point. We're deriving Euler's number E. The way you go about it is you say, okay, I'm going to give you 100% interest, and I'm going to compound that annually. And I want to start off with just $1, and I want to see how much money I'm going to have at the end of a year. Now, you might already know the answer. If I give you 100% interest per year, then after 1 year, I'm going to gain an extra $1. So in my mind, I know that I'm going to have $2 at the end of the year because I gave you 100% interest over that year. But I still need to go through the equation because we're going to make some changes along the way, and you'll see how we end up deriving with Euler's number E right here. So let's say that I'm going to give you 100% interest, and that's compounded, that's what comp means, compounded annually. That means only 1 time per year. All right, what did we get? And it's a $1 investment. Basically, I want to see how much my $1 grows whenever I do this. So the amount of money I'm going to have in the future is equal to the principal times 1 plus the interest rate over the number of compounding periods raised to the power then t. This is the same equation we wrote above. Here's how you go about calculating this. We know we're going to have $2 after 1 year, but let's just do it anyway. The number of dollars I have to start with is 1. Then it's 1 plus, what is my interest rate? I said it's 100% interest. Now, you never want to put 100 in. You never want to put the percentage in. You have to convert the percentage to a decimal. So if you take 100%, convert to a decimal, you move it 2 spots to the back. So you end up with 1.00. That's what you get when you convert 100% to a decimal. Shift the decimal spot 2 times. I'm only doing it annually. That means 1 time per year. I'm only doing it annually 1 time per year, and I'm looking down the road 1 year in the future. Again, if you don't know how this works, it's because you haven't watched my compound interest formula my lesson on that. So here we go. We have 1 on the inside. This is going to be 1 plus 1. So I'm going to have 2 in here, raised to the power of 1. Now you can see what's happening is I'm going to have $2, right? Because 2 times 1. That's what we get. And that's exactly what we expect. If I'm giving 100% interest compounded annually, I only give you the free money once per year, I only do the calculation once per year, then you expect after 1 year, I should earn 100% of what I had. And so I add them together, I get $2. That's what I get. So I'm going to go ahead and, I don't want to circle that actually, that's just an intermediate answer. Now let's change it a little bit. Now what happens if I do the exact same calculation? I still give you 100% annual interest rate, but now I'm not going to compound it annually. Let's compound it every 6 months. So every 6 months means you compound it 2 times per year. So for the next thing, what we're going to do, it's going to be 100% compounded every 6 months. But again, I'm only looking 1 year in the future, all right? So let's go ahead and calculate that. The amount of money I'm going to have is the principal times 1 plus r over n. I'm not going to write this every time, but I went ahead and did it this time. I'm investing $1. My interest rate is still 100%. I have to move the decimal, so I'll put 1.00, but I'm compounding 2 times per year, right? Put a 2 there. And then it's going to be 2 times per year here. I'm looking 1 year in the future. I just want to find out how much money I get if I compound it twice a year instead of once a year. Again, I'm looking over a 1 year period. So what I'm going to have is 1. This is going to be 1/2. 1 plus 1/2 is 1.5 raised to the power of 2. So if you do 1.5 square and you multiply it by 1, what you're going to get is 2.25. $2.25. So that, look at this is very important for you to understand before we go on. What's happening is if I tell you I'm going to double your money and I'm going to compound it only 1 time per year, you get exactly what you expect. I get double my money, right? But if I give you the exact same interest rate, but I compound it every 6 months, what this equation is doing is I'm taking that interest rate, I cut it in half because I'm going to give you half of the interest in each half of the year. I'm going to give you 0.5% or 50% interest really in 2 halves of the year. And so I'm going to do that smaller interest rate, 1.5, 2 times, 2 compounding periods in a year because I'm doing it every 6 months. So when you get this, you actually get a little bit more money than in the case whenever I just do it on a yearly basis. And that's a general thing that's true. If you keep the interest rate the same, but I compound it more frequently, even though the annual rate is the same, I actually make a little bit more money doing that. That's a general thing that's true for all calculations. But let's go on further. Let's say I have an incredible bank that's going to give me 100% interest. Let's do it even more often. Let's calculate how much I'm going to get if I compound monthly, right? So what if I give you 100% interest rate, that's what IR means, interest rate, compounded monthly. Compounded monthly. Let's see what we have here. So I'm going to have an amount that's going to be equal to the $1 that I spend, 1 plus the interest rate, still the 100% interest rate, but now I'm compounding 12 times per year. And up here I have the 12 times per year. I'm looking 1 year in the future, and so I need to calculate what I get here. So what am I going to have? I'm going to have 1. When you do the division here and add 1, you'll get 1.083 with a repeating decimal on the 3 raised to the power of 12. So you see what's happening? I took my 100% interest, but I chopped it up into 12 pieces because I'm going to actually compound it 12 times per year. So I take that 100%, but I split it into 12 equal parts, and I give that to you 12 times. That's what compounding means. I take the annual rate, I cut it into however many compounding periods I have, I cut it into a smaller number, and I give you that amount of interest throughout the year. That's what compounding is doing. This smaller rate is smaller than this one, which is smaller than this one because I had 2 right here, right? So I'm basically chopping the rate into a smaller piece, but I'm giving it to you more often. So what happens whenever I go through this is I get $2.61, $2.61. So notice when I compounded annually just 1 time a year, I got $2. When I did it every 6 months, I got $2.25. And whenever I do it every month, that's $2.61. So people like Euler wondered what would happen if I compounded even more often. What if instead of compounding, monthly or something like that, or even weekly, let's go and compound it daily. So I take that 100% annual interest rate and I chop it into 365 little tiny interest rates, and I give that to you every day. Would I make more money than this or not? And you can see the general trend is that I should make more money. So let's say that I take 100% interest rate and I compound it daily. And we do have real loans in real life that do compound daily. So what if we have that? We have $1 I'm investing, 1 plus the interest rate, which is still 1, but I'm dividing it into 365 pieces. And then I'm going to have 365 looking 1 year in the future. So you can see what's going to happen is it's going to be 1. On the inside here, when you do this division and you add 1, you're going to get 1.00274. This is rounded. when I divide that this is a rounded number, raised to the power of 365. So you see what happens is I take that interest rate that I was doing annually. I get a very small rate that's 365 pieces, right? But I'm giving that to you and I'm compounding that every day. That's why there's so many compounding periods. I'm giving you a little bit of interest every day rather than the whole thing over the whole year. What does this number come out to? Okay, what are you going to get? You're going to get 2.7146. Notice what's happening. As I increase the number of compounding periods, I go from $2 to $2.25 to $2.61 to 2.7146. I'm getting closer and closer and closer to a limit, right? Because notice that it was changing rapidly here, but then as I increase the point to the point where I'm giving you daily interest, daily compounded interest, the difference between this and this is not as great as it was over there. And you might have guessed by now that this number that I'm approaching is going to become the number E. But let's prove it to ourselves by taking this one step further. What happens if I don't compound monthly or even daily? What happens? Is it even possible to compound continuously? What if I compound every second? I mean, think about it. Then I would take one year's worth of seconds. There's got to be thousands of seconds in a year. I could go calculate what the number is. There's thousands of seconds in a year, right? But I could chop that interest rate into that many pieces, and I could do that many compounding periods. So this exponent would be really, really big, and this interest rate would be chopped up into even more pieces, but I would be giving you those more and more and more often. What would happen if I did it to the point where I did it down to the second? Or what about down to the millisecond? What if I took a year's worth of nanoseconds and then tried to figure out what this number is? What if I could do it continuously? What if I could shrink that compounding window down so close to zero that effectively it was almost quite zero, but it wasn't quite there, and I compounded what we call continuously? What would this number be in that point, in that limit? What would it be? And that's what we want to basically calculate now. So let's go off to the next board and do that. The equation that we would use to do that, 100% interest rate compounded continuously. That's what we're trying to do. The amount of money that I would have in the future would be the $1 that I would invest times 1 plus the interest rate. That never changed. But now, instead of dividing by 365 and then figuring out how many seconds in a year and how many milliseconds, I'm going to actually, instead of putting a number here, I'm going to put a number in down here because I'm just going to make it really, really small. And then in the exponent, it's going to be n times 1. This is exactly the same thing as I was doing here. Notice I had 365 and then 365 times 1. I had 12 here and then 12 times 1. Now all I'm going to do is I'm going to change it to a variable and then make it that same variable times 1. So what I'm going to end up getting is 1 times 1 plus 1 over n to the nth power. That's what this is. Okay. Now we said we want to compound it continuously. I don't really know exactly how to calculate it continuously, but let's try to get close as we can. Let's let n equal to 1,000 equal 1,000. So instead of compounding daily, where we have n is equal to 365 compounding periods in a year, let's increase it so that n is equal to 1,000. 1,000 slices of a year, that's how many compounding periods I'm going to have in a year. If I put 1,000 here, then it's 1 over 1,000 plus 1 raised to the power of 1,000 times 1. Then what ends up happening is the amount of money you get is 2.71692. All right. What if you let n equal to 10,000? I take a year and I chop it into 10,000 pieces. So I put 10,000 here and I put 10,000 here. I add this together, raise it to the power of 10,000. Then the number I'm going to get for the money is going to be 2.71815. Notice how it's getting close to some critical number here. Let's go to our last one, 100,000. 100,000 here, I chop the year into 100,000 pieces, I raise it to 100,000, and then the number that I get here is 2.71827. Again, very little difference between these. You can see as I increase the number n, I'm rapidly approaching some critical value. I'm never going to get past 2.8, right? So here's what you have. If you let n approach infinity. Infinity is not something you can ever get to. I can never get to infinity. If I think the biggest number I can think of, 1 billion, trillion, cajillion, bazillion, that's not even a number, but if I make it up, then I can always think of a bigger number. I just add 1 to it. So the number infinity is not a number, it's an idea. The number infinity is not a number. I keep saying the number infinity, it's a concept. It's the largest possible thing that you never ever get to. But we can still approach infinity by letting n get larger and larger and larger. But if we let n approach infinity, then what happens is the number e ends up becoming, by definition, what we call in advanced math, the limit as n approaches infinity of 1 plus 1 over n to the power of n. And this is approximately equal to 2.71828 ... And I'm going to go ahead and put in big letters that this is irrational. In other words, these decimals do not repeat. There's not a repeating pattern. I cannot write this number as a fraction. That's what that means. And because the mathematician Euler figured this out, this is called Euler's number. Okay. This is what you will see in a textbook. You'll probably see it in an advanced algebra book or an algebra 2 book. You'll definitely see it in a calculus book and an advanced math book. What it basically means is typically the definition that you will see is if you take the limit as n approaches infinity of this expression, you're doing exactly what we did up here. Start with 1,000 or something like this. Calculate the number. Go to 5,000, go to 10,000, go to 100,000, go to 1,000,000, go to 2,000,000, go to 5,000,000. And you're going to get numbers that get closer and closer and closer to the limit, is what we call. Now, how do we calculate this exact number is what this limit is. These methods to arrive at this exact number, of course, we could get closer and closer by picking numbers, but to know that this is the exact answer, those methods come from calculus. That's beyond the scope of this discussion. How do we actually calculate what the limit is? But you can see that these numbers are approaching this. In fact, we get to 2.71827. That's very, very close, up to 6 decimal places or something like that. So you can certainly get enough accuracy for a calculation just by doing it manually. But we know that this number goes on and on and on forever. We can calculate it with computers, and in the methods of calculus, we can find out what this limit actually is. This is what you will see in a textbook. Unfortunately, this doesn't tell you anything about why the number is important. You'll see it in a book that the number e is by definition equal to this, and is approximately equal to this, but it doesn't convey why it's important. The special number e comes about because exponential growth is when you take a number and you grow it exponentially over time, right? So if you pick the special case of trying to, if you pick the special case of compounding annually, where I'm going to double your money in a year, then that's exactly what you would get. If I take that same rule, trying to double your money, but I chop it up into 2 times a year, doing it every 6 months, I get closer to Euler's number. If I instead compound it monthly, again, giving you an annual rate of 100% trying to double your money, then I get a little bit more than double the $1 that I started with. And then, of course, as you go to 365, and as you get to 1,000 compounding periods and 10,000 compounding periods and 100,000 compounding periods, you end up with more and more and more money, but only up to a limit. So Euler's number is that limit. It's how much money you would gain if I offered you a 100% annual interest rate compounded every single nanosecond of the year. That's what it's basically telling you. You're going to get a little bit more than double your money, but it's only going to go up to a certain point, and that very special number is called Euler's number, 2.71828. I cannot express to you enough how important Euler's number is. It's basically impossible for me to do it because you haven't learned enough math to know how much this number pops up. But I can tell you with certainty that the number e pops up as much or more than the number pi, probably more than the number pi in all advanced math classes. All of wave interactions, sine and cosine waves that travel through space, that means all of our theories of light, all of our theories of oscillation, they all boil down to this number e, because all of those equations, sines and cosines, which we'll learn about a little bit later, they can all be written in terms of the number e. It's a very fundamental number that comes about as a result of exponential growth, just like the number pi is a very special natural number that pops out in the study of geometry of circles and straight lines. Okay. Now this is not a class on calculus, but I do want to do one more thing before we go and finish up everything here. And what I want to do next, let's see, what board space do I have? What I want to do next is I want to talk about, a little bit at least, why this number is so important. Okay. So E is special. Remember in the beginning I told you, I said that it's a very special number that comes about because of exponential growth. And so when we make an exponential function with E as the base, it's a special function. Because the inverse of this is the logarithm, the natural logarithm, which is the inverse of this function, okay, is also a very, very special number. Now, I want to take just a second to tell you a little bit why it's a special. This is not a class in calculus. It's not a class in advanced math. But I think everybody watching this can definitely understand why it's so special. And I want to take, it would be criminal for me not to tell you why it's special. So let's take a second to do that. Let's say we have the function f of x is equal to the number e to the power of x. We take that very special number that comes about when studying exponential growth and we make it the base of an exponential function, okay? What does this equation look like? What does this function look like if I were to graph it? So I'm going to go ahead and draw a graph. This is going to be freehand, so it's not going to be exact. All right, so it's not going to be exact in any way, shape, or form. So don't hate me, right? But anyway, if we have 1 and we have 2 and we have 3, let's say this is 1, this is 2, and this is 3. We know that this exponential function is going to go, let me use red. We know it's going to go through the point 1, 0, 1, because if I put 0 here, e to the 0, it's just a number. Number to the 0 power is 1, so that's going to go through that point. And we also know that the number e is actually 2.71, what did we say it was? 2.71828, so it's about 2.7. So this number is about somewhere right around here. This right here, this is where the number e is. It's about 2.71 is roughly equal to e. It's somewhere right around there. And so whenever I go and take a look at the number, this is 1, this is 1. So if I put the number 1 in here, e to the first power is just e. So this point right here, if I can draw it correctly, is going to be on the graph too. This number right there, right? Because if I put 1 in, I'm going to get e to the first power, which is e, and that's what e actually is. So this exponential function is going to go through both of these points, something like this. I'm going to do a terrible job drawing it, but I'm going to try. I'm going to go up like this, up like this, up like this, something like that. That's actually not too bad. So this is the famous function e to the power of x, right? E to the power of x. What is so special about this thing? You're not going to learn this until you study calculus later, but you can take a look at functions and you can figure out, you know how we talked about the slope of a line in algebra a long time ago? We said the slope of a line is rise over run. So it's easy to calculate the slope of a line. But what is the slope of this thing? I mean, forget about the actual number. You know the slope of this function is very high right here. It's very steep. And you know that the slope of this function is very low right here. It's very steep, very shallow. And as I travel along this curve, it's a very low slope. This is like a medium slope, and this is a very high slope. So the slope of this thing, whereas the slope of a line is the same thing, the same slope all the time, the slope of this exponential function is always changing. The slope is very low, close to 0 here, and the slope is very high. Maybe the slope is like 50 or 100 right here, and it's every number in between as I go. Now, the way that you figure out what the slope is of this curve, if you want to know what is the slope right here at this red dot, what you do is you draw a line tangent to this guy. You draw a line tangent. Tangent just means that it touches the red curve only in one spot, only at this dot right here. Okay? So what this very special function e to the x does is the slope of the line tangent, the slope of the tangent line, okay, at this point right here is equal to e. So that's something that kind of flies over your head if you don't study calculus, but I want to make sure you understand how incredible that is. What it's basically saying is this function, e to the x, is the only function so that wherever I am on the function, the slope of the function is equal to the value of the function itself. So right here at this point, the value of this function is e, right? But look at the dotted line, you go up, e to the power of 1 is e. The value of this function right here is e. And because the exponential function e to the x is very special, the slope of the line tangent to the curve at this point is e. It's the value of the curve itself. That's not true for any other function. When you look at functions in general, you can calculate the slope later on down the road in calculus. You can calculate the slope of the line tangent, but the slope is going to be whatever it is. You're going to calculate it using the methods of calculus. But the very special exponential e to the x is really the only function so that the slope of the line tangent is just equal to whatever the value of the function is itself. So let's say right here, the value of this function right here is 2. So if you were to go through and say, what is the slope of the curve right here? I'm not going to touch it because I'll mess up the ink, but if I say, what is the slope here? If you were to draw a line tangent there, the slope of the curve right here is equal to 2. It's equal to the same value of the function. What is the slope right here? The slope right here is 1. What is the slope right here? Well, it's whatever the value of the curve is down here. You can figure out the slope anywhere you want on this exponential function just by looking at the value of the function itself. It's the only function that really behaves that way. Okay. Now the other thing I want to talk about, let's plot the thing one more time. F of x is e to the power of x. And I'm going to do the same exact curve. Probably didn't give myself quite enough room. All right. But let's just do one more thing. Let's say 1, 2, 3. This is 1, 2, 3. And I'm going to do, now I can do a little faster. So I know that I have a dot right there. I know this is basically the number e. And then I can go right here and I can say this number is going to cross basically right here. Because if I put the number 1 into this equation, e to the power of 1 is e, which is right here. So this curve has to go up something like this. Hopefully I won't mess it up. I got to go through here, something like this. This is the curve. So I've tried to draw that thing freehand. Okay, another thing that's interesting about it, so the slope of the line that you get is equal to the value of the curve at that point itself. And also, if you look at this e to the x curve, the area under the curve, which is if I were to draw this thing and actually somehow physically measure the surface area, when I say the area under the curve, I mean literally if I could like pour a bucket of paint and measure how many square centimeters were underneath the area of this thing up to this point, then what I would find is that the area under curve up to this point right here is equal to the value of the point E. So the slope of any point on this curve of a tangent line is equal to the value of the curve itself. And the area under this curve up to this point, all the way from negative infinity all the way up to and including this point, is also equal to the value of the curve. So if I go over here so that I'm looking at the number 2 and then the value over here is e to the power of 2 or something like that, then the surface area underneath would be equal to whatever the value of the curve is at that point. So the interesting thing about this, and it's really the only function that behaves this way, is that the slope of a line, or the slope of the curve, at any point is equal to the value of the curve itself. And also the area under the curve, from negative infinity all the way up to any point you want to pick on that curve, the area under it is also equal to the value of the curve itself. So it's a really special function, and the reason it pops up that way is because the base of this exponential function is a very special number. It's the number that pops out by looking at the natural course of exponential growth. And so that's Euler's number. So these properties here, the fact that the slope of this curve is equal to the value of the curve itself, and the area under this curve is equal to the value of the curve itself at that point, those are crucial properties that we study in calculus. In fact, you study the slope of a line tangent to a curve for about the first half of calculus 1, and then the last half of calculus 1, you study areas under a curve. In fact, if I could boil calculus 1 down to one sentence, it would be you would study slopes and areas of functions. And because this function is so special in that the slope is always equal to the function itself, and the area under it is also always equal to the function itself, all of that will be proved later on in calculus. But because that is true, then this exponential function pops up everywhere. And because this exponential function pops up everywhere, also the inverse, which is the natural logarithm, also pops up everywhere. Okay? Last thing I'm going to leave you with is something that's just interesting that you might have heard, or some people read books or watch videos or whatever. there is the most voted equation. That's the most beautiful equation in all of mathematics. And it's not something we're going to study here, but I'm going to just present it to you and show you why it's so beautiful, and it involves the number e that we have been studying here. It's called Euler's formula. We're not going to study it, but we're going to look at it. Okay, Euler's formula is the following. E, that beautiful number e that we just learned, to the power of I, which is the imaginary number I, times pi, plus the number 1 is equal to 0. This is called Euler's number. It is very frequently discussed and talked about as being the most beautiful equation in all of mathematics, and this is the reason why. Euler's formula is an equation, because it has an equal sign, that includes the 5 most beautiful or core numbers in all of mathematics. Remember, I told you the number 0 was one of those beautiful perfect numbers. The number 1 was also one of those beautiful perfect numbers. The number pi pops up in geometry. The number I, the imaginary number, is extremely important. And the number e. And this equation relates all 5 of those core fundamental numbers together. If you grab a calculator and take the number e and raise it to the imaginary number I times pi, and you add 1 to it, you're going to get 0. So it's not something that we're going to do any problems on. It's not something I'm going to test you on or anything like that. It's mostly just trying to tell you why the number e, or at least one example of why the number e is so incredibly important. It even pops up in one of the most famous equations in all of math. So in this lesson, I really wanted to give you a background to where this number e comes from, this Euler's number, because I do get questions on it. We're going to study natural logarithms and exponential functions extensively, and I want to give you an idea of where it comes from. And the number itself is 2.71828, non-repeating decimals like this. We have some numbers that come from geometry, some numbers that are defined but are not geometric. But ultimately, the number e comes from the exponential growth of money, the compound interest formula. If you compound annually a 100% interest rate and then keep compounding more often to 6 months, to every month, to every single day, and then on to finally you go 1,000 times per year, 10,000 times per year, 100,000 times per year, you eventually approach this very special number e, which falls out of the exponential growth equations. And then lastly, when you take that number e and you raise it to the power of x, you get an exponential function with a base of e. This is stuff that you learn in calculus, but I'm just telling you what ends up happening is the slope of this curve at any point is just equal to the value of the curve itself. The area under this curve, from minus infinity up to and including whatever point you're looking at, is just equal to the value of the curve itself. And then finally, this number e is so important that it's involved in Euler's formula, which is one of the most beautiful and fundamental mathematical formulas ever derived. So it's really one of those fundamental numbers that pops up again and again. And when you go on to more advanced math, to advanced calculus, to differential equations, which is even more advanced calculus, you are going to see e pop up so often that your head's going to spin. It pops up more often than pi does. So I wanted to give you a background as to where it comes from. Now follow me on to the next lesson. We're going to study the natural logarithm in a lot more detail and do a lot more problems with the natural logarithm in math. Learn anything at mathandscience.com.